going to talk about the variable loading or fluctuating loadings or design of members against fatigue. So here is the outline of the class today. First, I'm going to introduce the fatigue topic. Then this will be followed by introducing the SN curve, which is very important in fatigue to just characterize the endurance limit or the fatigue endurance limit. Then we'll be talking, of course, about the endurance strength of the material that is normally found using this curve. This will be followed by the concept of stress concentrations. So if you have, for example, a change in the cross-section, so you have a small cross-section and then you have another large cross-section. So here there are some concentrations of stresses coming from small value to a large value. So we'll just explore this as well. We're going to explore also the notch sensitivity, where you will consider the material aspect. So in here, for this aspect, when we study the stress concentration, we focus only on the geometry, but in order to take the materials into account, so we consider what's called notch sensitivity, as you will see in a moment. Then we are going to talk about fluctuating stresses. So what type of stresses are there? Because these are the applied stresses, including sinusoidal loading, etc. So then we are going to talk about theories for fatigue failure, for direct stress, bending stress, torsional stress, combined stress, etc. This is towards the end of the class or the lecture. I'm gonna just focus more on the factors that affect the fatigue strength of the material. Okay. So here is the introduction. So so far, you've studied the static cases or static stress cases. We were focusing more on static loading or studying stresses based on static loadings. Okay, so simply you have just studied, for example, simply supported beams with like a non-time varying loads. So you have a beam, something like this, with a load F, where the force itself, if this is the time, this is the force. So the force does not change with time in this case. Okay, but here in real life, actually, this situation is hardly arise. So we have to consider fluctuating loads or time varying loads. For example, even for structures like bridges, so they experience this time varying loads because of the traffic flow and also the wind loads, etc. So for another example, for aeroplanes, so the wing of the aeroplane experience like time varying loads due to the flow of the air or the incoming flow, due to some turbulences, due to some shock loading during the landing and the takeoff. So also another example, so this is the second example. A third example is, for example, the axle of a car, where the car goes over humps or moves or over uneven roads. So those uneven roads or humps, they affect the axle, or they apply fluctuating stresses on the axle of the car. One example here, if we think about like fluctuating loads or reversed loads, if we think about an electric motor of a washing machine that we use, so the shaft of this electric motor rotates around 1,450 RPM. So in just 1 hour, if this motor is to work for 1 hour, so the shaft of the motor is going to rotate around 87,000 stress reversals. So it will experience this kind of stress reversals in only 1 hour. What I mean by that, just let's suppose that this shaft is exposed to a bending moment. So if this is like kind of the shaft and the load, let's just simplify this, say the load is in the middle of the shaft, and then this shaft rotates. So it's going to rotate with a specific RPM or with a specific rotational speed. So this point here, at one point in time, it's going to be here. And due to the bending, you see the bending here, the distribution of the bending is something like this. So we have tension here, and then we have compression, and at the neutral axis we have zero. So if it is tension and compression, so at this point, it's the other way around. So what we see here, we have tension here at the bottom, we have compression at the top. But after 180 degrees, so this point here is going to be just going to move downwards. So because the shaft rotates, when the shaft rotates, so this point will rotate and become here at this point. So in this case, it was at the beginning, it was under tension, and after 180 degrees, it becomes under compression. And the same applies here. It was at the beginning, it was under compression, and then after 180 degrees, this same point is under tension. So this means that in 87,000 stress reversal, meaning that if you pick a point on the surface of the shaft, so this point, just the stress on this point varies between tension and the compression with this same number of cycles. So for example, if this same electric motor or washing machine is used once per week for 1 year, so this shaft is going to rotate around 5 million cycles. So you see the scale of the stress reversal that one shaft or one application can see. Let me admit first, and then another example here. You see for second, another example here, or for the shaft of a gas turbine of a helicopter. So it rotates 36,000 RPM. So for example, if for only 2 hours flight, the rotor or the shaft of the gas turbine is going to rotate 3 million cycles. And you see each and every point, or the points on the outer surface of the shaft just goes through those stress cycles. So they see fluctuating loads all the time. So in this case, because of the stress reversals, they cause failure. And the problem with this kind of failure, that it fails at stress levels that is much lower than the one that we see for static stress. For example, if the same shaft fails under shear stress or under tensile stress, so we use the values that we get from uniaxial tension test, like the S yield, for example. So this is the or S yield in shear. So these are the values or the strength of the material, and we decide or define the level of the stress that we should apply based on these values. But in this case, when the stress itself, let's say we have time here, we have the completely reversed case, we have sigma, and then if we have sinusoidal load, so the load here or the stress varies with time, sinusoidally over time. So in this case, we have what's called the endurance strength SE that just governs the failure here in this case. So in this case, we have endurance strength of the material, or the fatigue strength of the material, or sometimes fatigue strength. And the fatigue strength of the material in this case is quite small. So this value, if you compare this value to this value, this value is quite small. So this means that we cannot just overload the material or stress the material beyond this value if we have fluctuating load. And the failure begins actually at minute flows. It could be something like machining scratch on the surface. It could be stress concentration. As I said on the previous slides, if you have a stepped shaft, for example, then at this point here between the small cross-section and the large cross-section, you have here a change in the cross-section. And due to this change, there are some stress concentration develops here, meaning that the stress is magnified. So if the stress here is sigma, for example, so at this corner here, so we have higher stress. I'm just gonna call this sigma naught, for example, and here sigma max. And there is a relation between these two, as we'll see in a moment. So normally the crack starts on the surface due to the fact that normally the maximum stresses on a component or on a shaft just appears on the surface of this component. If you have bending, if you have torsion, if you have tensile, and the tensile it's uniform, but for torsion and bending, the maximum stresses are normally on the outer surface. So once we have this minute crack, so it's under the application of the load, and this is kind of one example of the nature of the load. So the load starts to fluctuate. Then what happens is that the crack is going to grow. So the crack starts to grow under the application of loads or under the fluctuations of those loads. And also the stress concentration effect becomes greater in this case. The rate of crack propagation is determined by the level of the stress. So if you have high stresses, it means that the crack is going to grow faster. So if you have lower stresses, so the crack is going to be slow. But as the crack grows, what happens is that the cross-sectional area becomes smaller. And when the cross-sectional area becomes smaller, so it means that you have less area to carry the load. It means that the stress is going to be higher. And then eventually the crack will reach what's called the critical size. Once the crack reaches a critical size, so the part is going to fracture. So we have two distinct areas here. As you see here, maybe it's obvious here, you see this is one area, and this is the second area here. So this area here is just defined by having this kind of, they call it pitch, just the pitch marks. So we have some pitch marks here. So the top area here is where the crack propagates. So here the crack grows in this case, or in this portion. And then here, this part, this is the final fracture. So this is the fracture. So when you just explore the fractured surface of any fatigue fractures, you'll see these two kind of distinct areas. One area that shows like fracture or final fracture, and another area shows how the crack was growing and propagating through the section and starting from a minute just crack on the surface or inclusion in the material. So the first part, it is the propagation, the crack propagation, where the crack starts to propagate, and the second part is actually a sudden fracture. So the crack growth area, which is the first area here, which is this portion, this area here, it just shows a pattern. It's called this kind of sand pattern. That's why they call it peach marks, because it is similar to the peach marks on a peach. And this area denotes or shows how the crack propagates. So with each cycle of the load application, the crack propagates with a certain amount. That's why it just makes these kind of beach lines or beach marks. So for the second part, for this fracture part, so it is going to be, the nature of the fracture is going to be brittle fracture. It is going to be sudden and a catastrophic fracture for the towards the end of the propagation, the crack propagation. So once the crack reaches a critical size, so it just starts to fracture, or the brittle fracture happens without any sign at the beginning, before that. So the bottom part of the figure, the figure here, of this figure, this bottom part here, shows you the area of the fracture, or the fracture section. And even with like some ductile material, you see, normally we understand that brittle fracture occurs in brittle materials. But in this case, because we have fatigue loading or fluctuating loading, so this kind of failure or fracture happens. So the crack starts to propagate. It reaches like once it reaches its critical length, so the brittle fracture happens even for ductile material. So there would be no sign of any plastic deformation. If you look at the component, you would just feel like it's normal, nothing is wrong with the component, but obviously the crack just starts to propagate, and maybe if you don't do any inspection, you cannot see those minute cracks that are propagating with each and every cycle of the application of load. But when we reach the critical size of the crack, so the fracture takes place at the speed of sound in the material, and it happens immediately. It is catastrophic because the component fails without any sign. Then, for example, it depends on the application that you are looking at. So if we look at a bicycle pedal, for example, the failure of a bicycle pedal, so the failure or the fracture of this component is going to be inconvenient, just inconvenient, maybe just a little wound or something. But for components like an aircraft wing or tailplane or fuselage of an airplane, so if one of these components fail, it means a disaster. If we study the fracture of a rotating element or a rotating part in a factory, so if this rotating part fails, it means maybe massive damage to the machine itself or the neighboring machines. The production line is going to stop, some financial losses. So it depends. I mean, the consequences of this failure or fatigue failure depends on the application itself. So the figure that you see here shows an experiment that was done in the UK, at the Defense Research Agency in the UK in Farnborough. And it was for a section of a fuselage. And you see here you have a window, for an aircraft window. And you see here the damage that has happened on the left and the right-hand sides. So what happens here is that first, we have a square shape here for the window. So it means that for these corners here, there are some stress concentrations. So stress concentration because of these sharp corners, right? It is a stress riser. So it raises the stresses, it magnifies the stresses. Those sharp corners, they magnify the stresses. In order for this crack to propagate, we still need some fluctuating loads. Where does the fluctuating load come from here? It comes from just changing the pressure. You see, when jet flies or the airplane flies, depending on the altitude, so they keep pressurizing the fuselage from inside, just to maintain the pressure in the cabinet at the sea level, at the same pressure at the sea level. So it means that when the airplane gains or loses height, so they keep changing the pressure. They just either increasing the pressure or decreasing the pressure. And this is where the fluctuating stresses come from. So when the fuselage itself can be considered as a thin-walled pressure vessel, where the stresses vary with the height and the pressure that they maintain or they fluctuate or they alter inside the fuselage to maintain the pressure at around the sea level. So these fluctuating stresses, along with the square framed window, so they have introduced the stress risers or stress concentration or magnified the stresses, and hence this crack starts to propagate, and you can imagine lots of failures has happened, and the losses of lives, etc. So the fatigue or the failure due to fatigue just forms around 90% of mechanical failures. So 90% of mechanical failures that happen is caused by fatigue. So nearly all the materials, they fail by fatigue. Either it is metals, composites, polymers, ceramics, aluminum, even composites, all those materials can fail by fatigue. So based on this introduction and what you have seen, it is justified now to study or to try to understand the fatigue failure. Okay, so so how it all starts actually? It starts in 1900, where there was like repeated failure of railway axles in Europe. You see here the railway track, and here are the railway tracks, and you see here the railway axis, and it is subjected to some loadings, and it rotates at the same time. So this kind of stress or stresses that applied on this axle is fluctuating. So if this is the time, and this is the level of stress, so the stress here fluctuates or changes over time. So if you get the free body diagram, study the free body diagram of this axle, so you have an axle and then you have an applied loads here, let's call them W/2 each, and then you have some sort of reaction forces here. So a German scientist called August Wöhler started to test the fatigue of materials. This was in 1862. So what did Wöhler do? He just started to kind of invent or develop a testing procedure and a testing machine for this type of failure. So he started to, or thought about duplicating this kind of behavior. So you see here the axle is under bending loads or repeated bending loads or fluctuating bending stresses. So he's tried to replicate this kind of loading. So he came up with this machine. So on the right-hand side here, you have a motor that drives the specimen. And then this was followed by a counter for cycles. So we want here to understand after how many cycles this specimen is going to fail. And we have here a pivot and another pivot here. So we have these two bearings. So where the machine or the motor rotates here, and this shaft rotates, and then we have the specimen in the middle here. And then based on the other side, we have another bearing here and another pivot, so just to allow this rotation to happen, and also to allow for this loading to be applied. So we have here, eventually based on this loading, we have some sort of pure bending. So you have loading here, and you have loading here, and you have the specimen in the middle, and we want the specimen to rotate as well. That's why we have a motor, we have those kind of bearings, etc. So it just rotates. And then based on the loading, we have pure bending. So the standard dimension of the specimen, the smaller diameter here is 7.5 millimeter, and the specimen has to be carefully prepared. It has to be polished carefully to just avoid any cracks on the surface to propagate. And the load was applied as pure bending, as you've seen. And the specimen was driven by a motor, and we have a counter to just count how many cycles to failure. So as the load reduced, when you reduce the load, because here you see we have a load here. So when you reduce the load, it means that you have more number of cycles, or the specimen is going to stay or survive more. So if the specimen survives more than 10 to the power 7 cycles, so they normally stop the test, as you will see on the next slide. Do you have any questions, guys, at this moment? Are you unclear about anything before I move forward? And please, someone could say yes or no.
No, sir.
Okay. So based on the Wooler experiment, so this kind of curve can be obtained. You see here we have a fluctuating load on the x-axis, on the y-axis, and on the x-axis here we have the number of cycles to failure. This is one typical SN curve. S stands for strength, and N is the number of cycles. And what you see here, they keep just testing specimens. They just get like lots of identical specimens, and then they keep testing them at different levels of fluctuating stresses. So they change the stress level here. And when the stress level goes down, so it means that the specimen can survive more. So when sigma is small, so N goes up, okay? And then there are some points here, some important points in this kind of SN curve. The first important point is this knee here, where we denote this value here at this node. You see after this knee here, so regardless of the level of the stress, so we have infinite life. So at this point here, any stress that is less than the endurance strength, so at this point here, if the curve has this knee, so this level of the stress is called the endurance limit of the material. So if you have any stress, if you apply any stress on the material that is less than this endurance, so it will live forever without failure. So that's why here we say this portion here on the right-hand side of this point, we have infinite life. So any stress that is lower than the endurance strength means that the component or the part is going to just survive without any failure. But if you apply any stress higher than the endurance limit, let's say here, for example, so it will just survive up until this point. If you apply stress at this point, so it will survive up until this point. So it will survive a specific number of cycles, then it's gonna fail. So between the beginning here till this point, so we have what's called finite life. Finite life means that it's going to survive for a specific number of cycles, okay? But if the stress that is applied on the component is less than the endurance strength of the material, so it's going to survive an infinite number of cycles. Okay, so one more point here, one more important point is this 10 to the power 3 cycles. So if the stress level applied on the material just makes the material survive for 10 to the power 3 cycles or less, we call this is low cycle fatigue, LCF, low cycle fatigue. And if the component or the stress level makes the component survives for more than, excuse me, 10 to the power 3, so we have what's called high cycle fatigue. So high cycle fatigue, low cycle fatigue is between, depends on the 10 to the power 3 number of cycles. And this knee here depends on when we reach this knee, you see the line becomes flat. And then at this point, if you apply any stress, so it means that it will just survive forever. It's not going to fail. So this slide here says exactly what I said on the previous slide in terms of the knee point and the endurance strength of the material. So the endurance strength of the material is S sub E. This is the fatigue limit or the strength of the material in fatigue. Excuse me. So in this case, also, as I said, if the part fails less than or at less than 10 to the power cycles, so we call this low cycle fatigue. And if it fails at more than 10 to the power 3, so we call it this high cycle fatigue. The first point also is quite important. So if you here 10 to the power 0 is just one cycle. So if you load the material to its limit, kind of it's in with a stress level that is equal to its ultimate tensile or breaking strength, so the material is going to only survive one cycle. Okay, but any stress level that is lower than that, so the number of cycles is going to increase. It is worth noting here that the endurance, because in the graph here, in this graph or this figure, we've spoken only about the level of stress, okay? Level of stress. And we said that you decrease the level of stress, the number of cycles that the material can survive or the component can survive increases. And this defines in the end the endurance limit of the material. But in fact, the stress level is not the only factor that affects the endurance strength. There are other factors that affect the value of the endurance strength that you get out of those curves, including the surface finish. For example, if you change the surface finish of the specimen, so you would get different value for the endurance strength. If the material is tested at high temperatures or sub-zero temperatures, so you will get different value for endurance strength. If you have a corrosive environment, for example, even if you change the size, even if you change the size of the specimen, you see here, we have a standard, if I go back here, we have a standard shape and size of the specimen, which is in the middle here, it's the diameter is 7.5 millimeter diameter, it's polished specimen. So if you change the surface finish, if you change the size, if you change the temperature, if you use it in a corrosive environment, all these factors affect the value of the endurance strength. This just means one thing: endurance strength of the material is not an inherent property of the material. It's not similar to the elastic modulus, for example, of the material or the yield strength. So in this case, we have to take those factors into account when we just calculate or measure the endurance strength of the material. And you will see how we are going to take those factors into account. This curve here shows, again, we have stress here on the y-axis, and we have the number of cycles here on the x-axis. And the graph here shows you the SN curve for, or SN curves for different materials. For example, the first one at the top here is heat-treated alloy steel. The next one is medium carbon steel. The next one is aluminum or aluminum. The next one is cast iron. You see here for this one, we have the knee here for the heat-treated alloy steel. For the medium carbon steel, we have the knee point here. And for the cast iron, we have the knee here. So the knee means that if you apply a stress lower than this value of the stress on the material, so it will just, again, have infinite number of cycles and it won't fail. But there is a problem with aluminum, for example. You see here, it's just a straight line. So this C curve, it is just going downwards, downhill like this. So it does not have this kind of behavior. It does not have this kind of endurance limit or this knee. So it means that regardless of the level of the stress, it will eventually fail. So this will eventually fail. There is a problem here because aircrafts are mainly made of this aluminum alloys because of its strength to weight ratio. It's high strength to weight ratio. But in this case, so does it mean that it's gonna always fail? Eventually it's gonna fail, okay? And this means that aircraft components are quite dangerous. So what they do actually, so they see here fatigue cracks are grow normally in highly stressed parts like wings, tailplanes, or fuselage. But what they do, they just keep monitoring those cracks. They keep measuring the cracks. They don't want those cracks to reach what's called the critical size. Because once, as you've seen earlier, once they reach the critical size, they just fracture suddenly. So before they reach the critical size, they just replace them. And you see here, if I go back here, you see the last one was the cast iron, but you see the endurance, if you compare the endurance strength or the endurance limit of the cast iron, if you compare it to, for example, the endurance strength of the heat-treated alloy steel, you see the difference. So the cast iron here has an endurance limit, but it is very low compared to other steel alloys. I'm just gonna stop here for a moment.